Hi there, welcome to this lecture series on matrix algebra. This is lecture 16. The topic of this lecture is least square approximation, and this is part 1 of the video. In this lecture, we will cover the famous least square approximation, and we will view that as a minimization process with perpendicular projection, which is a topic we recently covered. And then we'll go through the derivation, and then in the end we'll give examples. Okay, so let's get started. Let's kind of motivate the algorithm and consider some linear systems with no solutions for a specific reason. So we consider a system of m linear equations with n unknowns. So you can write it as ax equal b. So here we are in the situation that m is much bigger than n. So this bigger than, if you put them side by side, this symbol here means this is much bigger than that. Okay. So which means that you have a small number of unknowns, but you have a large number of linear equations. So quite often there are no solutions. So if there were a solution x, then we have ax equal b, and that implies that ax minus b would be a zero vector. And so here we're in the situation that this can never be a zero vector. So if this can never be zero, then we look for the next best thing. That is, we, instead of solving this equation, now we try to find a vector x such that this quantity here is as small as possible. Here the quantity ax minus b is often called the residual, and you want to find an x such that the residual measured in certain norm is as small as possible. Okay, so we can now set up a problem equivalent to what we stated just here. So we seek to minimize the square of the residual, so the square of the norm of ax minus b, and we minimize it among all possible choices of x in Rn. Now, towards this goal, we will now write A in terms of its column vectors. So we are familiar with that. If A has column vectors, and then Ax would equal to the column vector times the x vector, and if you multiply it out, and you see that this becomes a linear combination of the column vectors with the xi's as the coefficients. So you add up like that. So we see that Ax will give you a vector which lies in the column space of the A matrix. Okay, so therefore let's now consider the subspace spanned by the columns of A. W is span of all the column vectors. Okay, so this include all the vectors A times x, where x is any vector in Rn. Now we see that if we want to find the best approximation, Ax equal b, where the b is not in the space W, then the next best thing to do is to find among all points in W, we want to find the one closest to b. So this vocabulary, closest to b, rings a bell. We have talked about this very recently. So from the discussion in the previous few lectures, we know that the closest point, this point here, would be the perpendicular projection of b on W. Okay, so here is a graphic illustration that you have W. Let's say we represent it with a plane. That's the span of the column vectors of A. and then we have a point B which is not in the space, and now we want to find its perpendicular projection. So you project this down perpendicularly and find the image P in the space W. And then this point P here will be the point in W that is closest to B. Okay, so this now means that we are seeking a vector P, which is A times X, which lies in the space W, such that we want B minus P to be in the perpendicular space W perpendicular. So that means B minus AX, because P is AX here. So B minus AX must be a vector that's perpendicular to all vectors in W, which means it's perpendicular to all the bases of the W, meaning V1, V2, and Vn. Okay, so we can write out what does it mean it's perpendicular. Well, that means the inner product is 0. So let's take a column I, we call the vector Vi. So Vi transpose times this vector B minus AX must be 0. That means these two are perpendicular. Okay, and then this equivalently, we can distribute the product into two terms. So VIT times B minus VIT times A times X equals 0, right? And then we can write the two terms must equal to each other. So that means VIT times AX, the second term, must equal to the first term, that's VIT times B. And this holds for every I, that is for I equals 1, 2, all the way to n. Okay, so we have found that we have this equation here satisfy for every I from 1, 2 to n. So basically, we obtain a system of n equations for the n variables for all the x's from x1 to xn. Okay, so we can now write it out in a matrix notation that will be the following. So we'll have every transpose of the column vector of A. So we put the column vectors here, and then A, we write it into column vectors, and then the x is the x vector, and then the right hand side is that's the transpose of the column vector. So we have this transpose, all the column vector lined up, times the B vector. So take a closer look at what we really have here. So this is just the A matrix written down in terms of the column vector. And what is this matrix? Well, that is exactly the transpose of this matrix, which is A. So this is A transpose times A times X equal, again, this is A transpose times B. So we can write it in a very compact notation like this. A transpose AX equal A transpose B. Okay, so let's define the least square approximate solution. So let's go back to where we started. So we want to solve AX equal B, and we found out we can't do that. And then instead of solving this, we seek the next best thing. You can say an alternative problem. We consider a problem that minimizes the residual AX minus B measured in certain norm square. Okay, and then this minimization process we just analyzed, and we derived that this leads to is equivalent to the system, the following system, that is A transpose AX equaled A transpose B, and then we need to solve X. Okay, so we call this problem 1, and we call this problem 2. So now just a few words of a caution here. So for problem 1, we see that this problem requires that AX minus B is 0. Okay, so which is very strict, and we cannot find a solution for that. And then, however, for problem 2 here, it only requires that ax minus b would be perpendicular to all column vectors of the matrix A. These are v1, v2, and vn. Okay, so this is a more relaxed requirement. Okay, and then okay, so we're not going to prove that, but I'll just mention it. And this fact, which is quite remarkable, is that the system 2 here will always have a solution, even when the system 1 does not have a solution. Okay, so quite remarkable. Okay, so let's take a look at an example and showing that the remark we just made. Okay, so let's consider system of two equations like this. x1 plus 3x2 is 1, 2x1 plus 6x2 is 5, which can be written as ax equal b, and we can collect the coefficient to form a. That will be 1, 3, 2, 6, which is here, and x vector equal the b vector. And it's easy to see that the system has no solutions, because if you multiply the first equation by 2, you will get 2x1 plus 6x2 equal 2, and then the second equation say that must be 5, so they're not consistent. Okay, so alternatively, we now seek a vector such that the residual measured in norm and the square of it is as small as possible. So we know this will lead to a different problem, and it will be the solution for the system at times a and x equal at times b. And we can put in the numbers, so that's A transpose, and that's A transpose, and that's B. And we work out the product, and we get this matrix here. That's the product of these two, and this product give me this vector. And then this system here is the system number 2. And we see that you see, if you multiply the first one by 3, you get the second one. So it is a system that has infinitely many solutions. You can pick x2 to be arbitrary c, and you can express x1 in terms of that. Okay, so we see that for a linear system with no solutions, we formulate it into the least square problem and having a new system here, and this system has solutions. Okay, let's take a closer look at the solution. So solution is x2 is c, arbitrary, x1 is that, and what does that equal to? Well, this means the projection is now x1 times column vector 1 from A plus x2 times column vector 2 from A, right? And then we put in the expression of x1, which is here, and then x2, which is c, and then we add up these two vectors, and we see that the term containing c will be cancelled out. So all you have is 11 over 5, which is the scalar number, times the vector 1 over 2. Okay, so a closer look, you will see that 3c times this vector 1 and 2 is exactly negative of this vector, so they cancel. So we see that even though the solution has an arbitrary constant c for the x1 and x2, the projection here, p here, actually is the same for all the choices of that constant c. So it's not surprising, right? Because if you have a vector b and you do a perpendicular perpendicular projection onto a subspace, there is just one projection point. Okay, so W is the span of the two column vectors, and which means they are the same. That is, it's just the span of 1, 2. So that is a line. So you're projecting the vector B onto a line, and there is just one point. Okay, so that's all for part 1 of this lecture. In part 2, we'll give some more examples and make some discussions. Okay, so I hope you enjoyed this one, and I'll see you soon.